Hello everyone, welcome to EGN 3343 Thermodynamics, and today we are going to change topics completely to introduce the second law of thermodynamics. Remember that up to this point we've talked about, well, the zeroth law of thermodynamics, which is basically thermal equilibrium. It's basically the macroscopic definition of temperature. We talked about the first law of thermodynamics, which is basically an energy balance. It's the conservation of energy. And we talked about it from an open system point of view and a closed system point of view. So on the analysis of problems under the control mass or the control volume point of view. Now, most laws in physical sciences come from a conservation principle, a general and universal conservation principle, such as the first law of thermodynamics, for example, comes from the conservation of energy. You establish the fact that energy is transmitted into a system and it's taken out of the system. It can also be generated and it can also be stored. Then you equate these quantities, and depending on from what frame of reference you're looking at the system, you end up with an equation. The case of the second law of thermodynamics is completely different, because the second law of thermodynamics does not come from a conservation principle. It is not formulated from a conservation principle. The second law of thermodynamics is just simply a series of statements and corollaries that come from direct observation of the functioning abilities of different thermodynamic systems, such as, for example, heat engines. So today what we're going to do is formulate these corollaries, these statements, and then talk about their applications or their implications into the observation of the functioning of heat engines, for example, and to the how they affect the operation of heat engines. Obviously, we are going to define what a heat engine is. We are going to define the efficiency of heat engines. We're going to talk about, once we introduce the statements and corollaries, we're going to talk about what formulas do they lead to. So there's not a major formula for a second law of thermodynamics. As I said, just observations that lead to statements and corollaries. And at the end, we are going to come up with some formulas to try to establish limits to how things can happen in the real world. That's what the second law of thermodynamics is about. So we basically start by looking at empirical observations concerning energy transformations. So there are observations that lead to the implications that there are certain things that occur in certain ways as to establishing limits in the way energy is transformed in a system. If we see, for example, how an ice cube melts inside a cup of tea, a cup of hot tea, and we looked at that process as a thermodynamic process, and we try to analyze it not from the point of view of, well, how does the ice cube actually melt, but how would you actually do the opposite, or can you do the opposite? Can you have water mixed with tea, for example, and then try to make ice out of the water only mixed in the tea? Can you reverse that particular process? Is it difficult? Is it complicated? Will it require the same effort? Let's say that we have two tanks at different levels. If we open a valve between the tank, then they'll lead to equilibrium. Can we actually reverse that process by pumping one liquid into the other tank and getting back to the initial condition? Does it require the same type of effort? If we have a tank at high pressure and a fluid inside a tank at high pressure, and we open a valve or we just basically rip a hole in the tank, that escape process of the fluid at high pressure, what type of process is that? I know, or we know, that by observation there's going to be thermodynamic properties at play. Things are going to change. The pressure is going to change, certainly, during the process. The temperature is going to change. But can we reverse that process? Can we actually conceive a process that will take us from the final state to the initial state? And what type of effort that we have to effect? And in general, the conversion of heat input into work output, which is essentially how we create power in a thermodynamic process. We use heat in order to create work, and that's the basic energy transformation that takes place in power cycles or heat engines. Now, as I said, the second law of thermo is not a formula. It doesn't come from a conservation principle. It's not a general or universal conservation principle. It's just a series of statements and corollaries that come from observation, from empirical observation about processes, about energy processes. Some of these corollaries or statements are known as the Clausius statements, and the other one is the Kelvin-Planck statement, which will list and try to define and explain and interpret from a thermodynamic point of view. The Clausius statement is very simple. It says basically that it is impossible for any system to operate in such a way that the sole result would be an energy transfer by heat from a cooler to a hotter body. Okay? It doesn't say that it's impossible to transfer heat from a cool body to a hot body. It doesn't say that. It just says that it's impossible for a system to operate in such a way that that would be the sole result. You can accomplish that, but there's got to be other things in between. You can have a hot body and you can have a cold body, and somehow you can actually extract energy from the cold body, and somehow you can actually send energy to the hot body. But in that process, there's got to be other things that take place, like other processes, other internal processes, and other exchanges that take place for that to happen. So that cannot be the sole or end result or only exclusive situation taking place in that particular thermodynamic process. Okay, so that's going to lead to other consequences. In order to define those consequences, let's define what a thermal reservoir is. Okay, a thermal reservoir is a special kind of closed system from which any finite amount of heat may be removed without changing its temperature, or to which any finite amount of heat can be added without changing its temperature. So think of a thermal reservoir as something at a constant temperature. Okay, it's something at a constant temperature, but it's so big that you can actually add as much heat as you want, finite amount of heat, and the temperature will not be affected. Or you can subtract the amount of heat that you want, and its temperature won't be affected. For example, the atmosphere is a classical case or example of a temperature reservoir or a thermal reservoir. Because let's say that the atmosphere outside my office right now is at 70 degrees Fahrenheit. It doesn't matter how many thermal or thermodynamic processes go on, for example here in my office, or with the air conditioning going on here in the office building, or any situation that goes on, or if I turn on my car. I know that if I turn on my car, there's going to be combustion gases going into the atmosphere, but that's not really going to change the temperature of the atmosphere. Only my car will not do that. Maybe 1 million cars will do that, and it will do that on a localized fashion. But just turning on my car will not change the temperature of the atmosphere. So the atmosphere is essentially a very common case or example of a thermal reservoir. It is at 70 degrees in the case that we're analyzing right now, and we assume it is going to be at 70 degrees, even if we dump an enormous amount of energy into it, or if we subtract an enormous amount of energy from it. Okay, so that's the notion or definition of a thermal reservoir. It can also be a hot temperature reservoir. Say, for example, that you're boiling water in a boiler, and in order to do that, maybe you're burning gas. Okay, so you burn gas, and we know that depending on the type of fuel that we're using, gas is going to burn or ignite at a certain temperature. So that certain temperature is going to create a local hot temperature reservoir, which means that that amount of gas or that amount of fuel is going to give heat away to the system, to the boiling water or whatever, and that igniting fuel is not going to change its temperature in the process of doing so. So that can also be considered a thermal reservoir. So we have cold reservoirs, we have hot reservoirs, and depending on their temperature and the relationship of that temperature with the system temperature, we use it for something different. Now that leads to the Kelvin-Planck statement, which essentially says something simple. It is impossible for any system to operate in a thermodynamic cycle and deliver a net amount of work to its surroundings while receiving energy by heat from a single thermal reservoir. That means that you at least need 2 thermal reservoirs in order to produce energy in the form of work, in order to produce work. We know that a thermodynamic process of creating work is essentially the transformation of heat into work. Okay? How much of that heat can we transform into work? Well, that depends on what we're doing, and obviously lead to the efficiency of that thermodynamic cycle. Remember, again, a thermodynamic cycle is a series of processes that will take you to the initial state. Okay, that's the definition of a cycle. Now, in order for you to create a positive net amount of work out of that cycle, that working fluid in that system needs to exchange energy with at least energy in the form of heat with at least 2 thermal reservoirs, not only with one. Which means that at some point during the cycle it has to absorb energy, maybe from a fuel, burning fuel, and at some point in the cycle it has to reject energy, maybe to the atmosphere. And that's what happens in all power cycles. In order to create work, you need to absorb energy, but that's not enough. You also need to reject energy somewhere in order to produce a positive net amount of work. So you need at least 2 thermal reservoirs in order to do this. And it sounds very simple, but it's actually a major consequence. It has major consequences in the definition of efficiencies and the definitions and the formulation of the second law of thermodynamics. Now let's talk about reversible processes and irreversible processes. Okay, and what are they, and what is the implication of a process being reversible or a process being irreversible? One of them is a restrained expansion or compression, and we've gone through this. A restrained expansion or compression. Basically, if you have a piston cylinder device or piston cylinder assembly, and you have a limitation as to where the piston can actually move, compress, or expand. And while it's restrained, either by net weight or maybe by springs or any other type of contraction, you can always consider these to be a reversible process. Frictionless motion. Any motion of any body over any surface that occurs frictionless leads to a process where there's no dissipation, no hysteresis, and therefore no irreversibility. So that is a process you can consider to be reversible. And in essence, reversal or reversibility means that you can actually reverse the process, go from the final state to the initial state, applying the same amount of effort, but inversely. Elastic stretching of a solid. So as long as the solid that you're stretching is done within the elastic limit, as long as the solid doesn't yield, that process is reversible. If you have an electric circuit with zero resistance, we know that the imposition of a resistance in an electric circuit is going to lead to heat dissipation. And the heat dissipation, if it's uncontrolled, is something that is not reversible. It means that you cannot take that energy in the form of heat, put it back into the resistor, and create the current that passed through it. It simply cannot be reversed. Polarization and magnetization effects are also a typical example of reversible processes. Restrained discharge of a battery, by the same argument that a restrained expansion or compression can be reversible, then restrained discharge of a battery can also be reversible, because then you can charge the battery using the same amount of effort, but the other way around. Now, there are also internally reversible processes. These are processes that are not totally reversible, but at least the reversibilities can be confined. That means that the irreversibilities can also be confined. This is a process which is reversible within the system, but the irreversibilities can be confined to the boundaries of the system. That means that you can say, well, the process internally occurs reversibly, and everything that is lost and everything that it cannot be accounted for, all the hystereses, all the dissipation, can be accounted for through the boundary. Okay, so that helped. That would actually help enunciate and formulate a lot of the equations and a lot of the principles that we are going to treat using the second law of thermo, by stating that a process, although it is irreversible, all the irreversibilities can be confined to the boundary, so everything within the system is reversible, and these equations apply. So most processes we'll treat in thermodynamics are internally reversible, and we just simply call them reversible. When we treat an internally reversible process, we just simply say it is a reversible process. Now, irreversible processes are processes that occur internally irreversible and irreversibilities through the boundaries as well. So there's no way that we can have this process occur in a reversible form. The process of dissipation through an electrical resistance, the process of inelastic deformation. Once you yield a solid, you cannot take it back to the elastic region. It already yielded. Shock waves, for example, are a typical classical example of an irreversible process. Hysteresis effect, in general, anything that cannot be accounted for is called hysteresis. Viscous flow of a fluid. Well, the viscosity in a fluid acts as an electric resistance, basically, is lost due to friction and of the motion of fluid, or is the opposition to the motion of a fluid. Internal damping of a vibrating system, for example, is also an irreversible process. It leads to dissipation. Solid-solid friction, more irreversible process. The unrestrained expansion of a fluid. Fluid flow through valves and porous plugs or porous media. That is a typical example also of a fluid, of a process that cannot be reversed. Spontaneous chemical reactions. If a chemical reaction is exothermal, you cannot use that energy again to actually put the go back to the initial elements in the chemical reaction. And mixing of the similar fluids is usually, obviously, a very irreversible process that cannot be reversed. If you have two dissimilar fluids and you mix them, it might take very little effort, but try to separate those fluids, it will take major effort. So that difference between the effort involved in doing something and doing something in reverse is just explained through irreversibilities. Okay, so now let's define a heat engine. And heat engines have been around for ages, and they have been used to produce energy for ages. Not only during the Industrial Revolution, that's when heat engines were put to work, but even before the Industrial Revolution, actually at the time of the ancient Greece, there were such things as heat engines, not for the purpose of what they're used later, but they existed. Now, they were not necessarily understood. Many mathematicians and physicists tried to explain at the time the operation of these devices and try to quantify how much you can produce with it, how much you can extract from it, and that actually led to some conclusion or conclusive remarks as to the operation of heat engines, but never something that had scientific basis or something that had some principle behind it other than just plain observation. So it wasn't until maybe during the French Revolution when a French general, actually, I don't remember if he was a general, he was in the French army, Carnot. He was an engineer of the French army, and he was commissioned with analyzing heat engines, and for the purpose of increasing its efficiency. Okay, how can we, in order to be able to know how much we can extract from a heat engine, how much power we can produce, we need to understand first how it works. We need to define it. We need to quantify it, and we need to set up some parameters in order to then know how can we optimize it. So Sadi Carnot was his real name was not Sadi. Sadi was his third name, and so he was known by that name, Sadi. He was commissioned with these, and he is known as the father of thermodynamics because he was actually the one who organized his ideas and set up these principles. And he started by the observation of heat engines. How do they work? Well, a heat engine is a device which operates continuously or cyclically. So basically, a heat engine is something that has a thermodynamic cycle. So a thermodynamic cycle is going on, and that is usually, of course, a power cycle, not a refrigeration cycle or a heat pump cycle. It's got to be a power cycle. So there's got to be a positive amount of work, of net work, produced at the end. So it produces work while exchanging heat across its boundaries. And we already know this. A cycle is a collection of processes that will take you to the initial state. It is a power cycle if the net amount of work is positive. And in the process of doing so, there's going to be some Q in and there's going to be some Q out. Maybe multiple processes will involve Q in, heat absorption, and maybe multiple processes are going to involve Q out, heat rejection. But we are definitely going to have some Q in, and we are definitely going to have some Q out. Okay? Now, as an example, let's see, for example, this piston cylinder device containing a gas, and we have constrained motion. And let's see, and again, this is an academic example of how to produce work with a piston cylinder device. For later, we are going to actually look at the real applications piston cylinder assemblies and what are the different types of cycles that lead to the generation of work. So let's assume that we have this gas under thermal equilibrium, so it's in thermodynamic equilibrium, and then we slide a weight across its top, across the piston. That particular process is an isometric process. The process of sliding a weight from point 1 to point 2 across the piston is theoretically an isometric process because the volume doesn't change, and it's a process of increasing the pressure of the gas. The more weight we add to the top, the more pressure there's going to be inside the gas. And we are going to do so slowly, so that it's a reversible process. It's a quasi-static, and we're going to try to do so reversibly. Okay? Meaning that the process of sliding the weight from point 1 to point 2 is the same thing as sliding the weight from point 2 to point 1, the effort involved in that. So that's going to lead to an isometric process of increasing the pressure. Okay? So we are going to increase the pressure isometrically. Then we are going to expose the gas inside the thermodynamic system to a hot temperature reservoir. Okay? So this is a thermal reservoir at a temperature that is higher than the temperature of the gas. If the cylinder is exposed to that, then there's going to be an exchange of energy. Assuming that the piston is not thermally insulated, there's going to be an exchange in energy. And that exchange in energy is going to occur in the form of heat from the hot temperature reservoir over to the gas. In the process of doing so, the temperature of the gas is going to tend to increase, and then therefore the pressure of the gas is going to tend to, not the pressure, but the volume is going to tend to increase. The pressure cannot increase because the pressure is constrained by the weight that we put on top of the piston. The weight divided by the cross-section area of the piston is going to be simply the pressure inside the cylinder. So the pressure is not going to change. So by exposing the gas to a hot temperature reservoir, we are going to effect energy transfer in the form of heat from the thermal reservoir over to the gas, and the temperature of the gas is going to tend to increase, and by doing so, the volume is going to tend to increase. So this piston is going to raise to the top. The process of raising the piston from the bottom to the top is an isobaric process. It's an isobaric expansion process. It is isobaric because it occurs at constant pressure. Then we remove the hot temperature reservoir, or we take the piston cylinder assembly and remove it or move it away or isolate it from the hot temperature reservoir, and just simply slide the weight outside the piston. The process of sliding the weight out of the piston is a constant volume process. It's a pressure decreasing constant volume process. Basically, the volume of the gas, the volume of the cylinder in which the gas is contained remains constant, and the process of taking the weight from the top of the piston out of the piston can be considered a constant volume pressure reducing process. Okay? At the end of this process, we're going to have a lower pressure because the weight of the piston is obviously less than the weight of the piston plus the weight that we added to it. Then, after we have these at lower pressure, at high volume, lower pressure, we expose this piston to a cold temperature reservoir, another reservoir. Okay, this is just a schematization of what's really going on, an illustration of what's going on. The cold temperature reservoir can be the atmosphere. Now we have gases inside this piston at high temperature. We expose them to a cold temperature reservoir, and because the cold temperature reservoir is colder than the gases inside the cylinder, there's going to be energy transfer in the form of heat from the gases over to the cold temperature reservoir. So this is a heat rejection process. It is a heat rejection process, and during that process, the temperature is going to tend to go down, and as it goes down, the volume goes down. So this piston is going to lower all the way to the bottom stops in a very slow process. This is a constant pressure process, notice, because the piston weight doesn't change. So during the entire process of compression, the piston goes down, but the piston goes down at constant pressure. The pressure inside the cylinder is the same. And it's a process through which we are exchanging energy in the form of heat rejection, over to a cold temperature reservoir. And that leads back to the initial state. So we basically have four processes. Okay, this very simple illustration of a heat engine, which is nothing but a thermodynamic cycle, power cycle, is a process by which we increase the pressure at constant volume. That's the process of sliding the weight in. Then we increase the volume at constant pressure. That's the process of raising the piston and the weight together by putting it in contact with a hot temperature reservoir. Then the process from 3 to 4 is a constant volume pressure reduction process. That's when the piston is on the top, we remove the weight. By removing the weight, we're lowering the pressure, but it's occurring at constant volume. And then we expose the piston to a cold temperature reservoir, and by doing so, we reduce the volume back to the initial state at constant pressure. So the piston goes down at constant pressure inside the cylinder, and we regain the initial conditions. So this constitutes a power cycle, a very simple power cycle that is just academic. It's just theoretical. It's very difficult to implement this in practice, to implement this idea of having a weight and moving it on top of the piston and taking it out. It's very unfeasible. It's also very impractical. Okay, you cannot do that and do it over 1,000,000 times and expect to produce a net amount of work. And then moving a hot temperature reservoir in and then moving a cold temperature reservoir. We need to have practicality. And practicality would probably entail or involve completely different processes that lead back to the initial state. Okay? Okay, so it seems like we are deviating away from the purpose of this lecture, which is defining or enunciating the second law of thermodynamics, but we are not doing so. In order to define the second law of thermodynamics, we need to explain what a heat engine is, and it's basically, remember, a power cycle, a thermodynamic power cycle. So knowing what a heat engine does, and knowing that it needs to exchange energy due to the Kelvin-Planck statement, it needs to exchange energy with at least 2 thermal reservoirs, let's look at the corollaries of the second law, and these corollaries were stated by Carnot. The first corollary says that the thermal efficiency of an irreversible power cycle is always less than the efficiency of a reversible power cycle when each operates between the same thermal reservoirs. Okay? It's very simple. If you have a power cycle that is being produced by a heat engine, and this power cycle is operating between 2 thermal reservoirs, a cold and a hot, or a cold and a hot, and the processes within that power cycle are reversible, so every single one of these processes occurs reversibly. This leads to an efficiency. Efficiency, basically, remember, is the amount of net work that you obtain from the cycle divided by the amount of heat that you have to put in to the system. Only the heat in, not the heat rejection, but the heat in. So that's the efficiency. Now, if at least one of the processes is irreversible, then the efficiency will be decreased. So this establishes the limit to the efficiency of a thermodynamic cycle. Okay? We know that the efficiency limit is 100%, but that's impossible. So within 2 thermal reservoirs, there's got to be a limit to the efficiency that you cannot really obtain in actuality, and that is established by this corollary. And it's not 100%; it's somewhere below 100%, and that is the limit. You cannot produce more than that. So this basically means you had a hot temperature reservoir, you have a cold temperature reservoir, and you have 2 engines, 2 heat engines. One that's reversible, which basically means that it can do exactly the opposite with the same amount of effort, but in reverse. And this is producing some reversible amount of work. And there's exchange of energy with a hot temperature reservoir, we call it QH, essentially Q in. And there is exchange of energy with a cold temperature reservoir, we call it QC, which is essentially Q out. It produces a net amount of work, which is essentially QH minus QC due to the first law of thermal, remember. In a cycle, you can actually eliminate the delta U from the first law of thermodynamics, and you can say that the net amount of work is equal to the net amount of heat. And you can divide the net amount of heat into Q in minus Q out, or in this case, QH minus QC. Okay. Now, if at least one of the processes going on inside that heat engine is irreversible, or all of the processes in that heat engine are irreversible, then the net amount of work that will be produced, the W irreversible, is going to be less at the end of the day. Or at least the net amount of work that you are going to draw from the hot temperature reservoir is going to be less. It's going to be higher. I'm sorry. The net amount of heat required is going to be higher in order to produce the same amount of work. So either one of the two. Either the net amount of work is less on an irreversible cycle, or the net amount of heat that you extract from the hot temperature reservoir has to be more. And that would lead to a lower efficiency. Remember, the efficiency is W divided by Qn, which in this case is QH. W divided by QH. So that is the first corollary of the second law of thermo as enunciated by Carnot. The second corollary says that all reversible power cycles operating between the same two thermal reservoirs have the same thermal efficiency. Okay? That's just a corollary due to observation. So he took different power cycles, different heat engines, operating within the two same temperatures, and as long as they operate reversibly, they will yield exactly the same thermal efficiency. So they will produce or yield exactly the same ratio of work to heat in. Right? So this is the second corollary. If you have two reversible power cycles, they both can be operated reversibly, and they're both operating within the same two thermal reservoirs, we know that Qin is going to be absorbed from the hot temperature reservoir, and Qout or QC is going to be the heat rejected from the system over to the cold temperature reservoir. In the process of doing so, we're going to generate a net amount of work called WR. If we do so with a completely different heat engine that operates with completely different processes, but it returns back to the initial state, this will yield the same amount of efficiency, the same number for efficiency. That means that the ratio of W over QH is going to be the same. Okay? So that is a consequence of the observations, and that's how he stated his observations of heat engines into these two corollaries. Now let's look at the implications of these two corollaries. First of all, remember the definition of thermal efficiency. The thermal efficiency, which we call eta TH, or thermodynamic efficiency, or just thermal efficiency, or just eta, is the net amount of work being produced divided by the amount of heat that we put in. This is the cost of producing work. It's the net amount of heat that we put into the system. Okay? We can put it in by burning fuel, so it's the cost of the fuel, etc. We can put it in by other chemical reactions or nuclear reactions, but this is the investment into the power cycle. And this is what we obtain out of the power cycle, W net. The purpose of a power cycle is to produce work out of heat exchange. Now we know that the W net is going to be less than Wn, because if we apply the first law of thermodynamics to the entire cycle, we know that the W net is equal to Qin minus Qout, okay, minus the absolute value of Qout, where Qout is the heat rejection to the cold temperature reservoir. Qin is the heat absorption from the hot temperature reservoir. So basically, since W net is Qin minus Qout, you can define the efficiency of the cycle as Qin minus Qout divided by Qin, or basically 1 minus Qout divided by Qin. Again, the absolute value of Qout, because Qout is actually negative. It leaves the system. Heat rejection is negative, so we use the absolute value. We're already establishing that it's negative by forcing the negative sign here and then putting in the absolute value of ours. So this is the thermodynamic efficiency of a power cycle. 1 minus Qout divided by Qin. In the case of the ones that we're illustrating in this class, Qout is going to be QC, is a heat rejection to the cold temperature reservoir, while Qin is QH, is the heat absorption from the hot temperature reservoir. Now, if we look, this is not a consequence or an implication of the corollaries of Carnot. Okay, this is just the definition of thermal efficiency of a cycle, which we've used before, even long before we knew about the second law of thermo. Now let's use the second corollary, which says that two reversible cycles operating within two thermal reservoirs, the same two thermal reservoirs, will yield the same efficiency. Which means that if the cycles are reversible, the efficiency has to be only a function of TH and Tc. They're only a function of the temperatures of the hot and the cold temperature reservoir. Okay? Because, as Carnot stated, through his observations, basically, if you have the same two thermal reservoirs and the two cycles are reversible, you will always yield the same efficiency. It is a reversible efficiency. It's essentially unattainable efficiency because you can never get that close to perfect reversibility. So this leads to a very simple relation, which it doesn't lead to this relationship. This relationship at this point is just an assumption. We are going to assume that the ratio of temperature cold by temperature hot is equal to the ratio of the heat that we absorb from the temperature cold to the heat that we reject, or the heat that we absorb from the hot temperature reservoir and the heat that we reject to the cold temperature reservoir. And basically we're missing absolute value bars around QC, but we just assume that it's the magnitude. So therefore, the thermal efficiency of a reversible power cycle is 1 minus, which was 1 minus QC over QH. Now we established that it's 1 minus DC over TH. This is also called the Carnot efficiency. So the Carnot efficiency is the limit efficiency of a power cycle. It's the maximum efficiency that a power cycle can attain when it works in the ideal form, reversible. Okay? So a reversible power cycle can attain a maximum efficiency of 1 minus the temperature of the cold thermal reservoir divided by the temperature of the hot thermal reservoir. Okay? And those temperatures have to be obviously in absolute temperatures, in Kelvin or Rankine. They cannot be in Celsius or Fahrenheit. This is called the Carnot efficiency. So let's remember this equation, because this equation is essentially the first equation that we have enunciated from the second law of thermodynamics. The second law of thermodynamics, if you can summarize it into a simple equation, is just simply the Carnot efficiency. The ideal efficiency, or the maximum efficiency, also called the Carnot efficiency, is the efficiency of a reversible thermodynamic cycle. It's 1 minus T cold divided by T hot. So if we know the temperatures of the hot and cold temperature reservoirs, we can calculate the maximum efficiency that that cycle can attain. Any other efficiency of that cycle will be less due to irreversibilities. Now, using the same exact arguments, we can establish the coefficient of performance of a refrigeration cycle. Remember that in a refrigeration cycle, the purpose is to extract energy from a cold temperature reservoir. So you want to subtract energy maybe from a cold room like this one. My room right now is at, let's say, 65 Fahrenheit, and the atmosphere outside is at, let's say, 90 Fahrenheit. So my room is a cold temperature reservoir. The atmosphere is a hot temperature reservoir. My room is at 65. The atmosphere is at 90, let's say, just to put a number to it. So my room is acting as a cold temperature reservoir, and the refrigeration cycle going on, which is some refrigeration system sitting somewhere, and there's some pipes going through my room, extracts energy from this room and then rejects energy to the hot temperature reservoir. So it does the opposite. It subtracts energy from the cold temperature reservoir and it dumps or rejects energy to the surroundings. And it does so by using work. So this is the opposite. We are transforming mechanical work into heat. So using the same argument that we use for Carnot efficiencies, we can use it for the coefficient of performance of a refrigeration cycle. If the coefficient of performance is QC divided by W, and the W net of the cycle is QH minus QC due to the first law of thermodynamics, this is Q out, this is Q, this is Q in, this is Q out, this is Q in. Therefore, using the same type of argument and using the same ratio of temperature of the reservoirs to heat extracted and rejected over to the reservoirs, the maximum theoretical coefficient of performance of a refrigeration cycle is temperature of the cold reservoir divided by temperature of the hot reservoir minus temperature of the cold reservoir. So we can directly calculate, for example, what would be the maximum efficiency that you can attain, not efficiency, but coefficient of performance that you can attain by installing a refrigeration cycle to cool down this office by calculating, well, what is the temperature that I want in this office? Let's say 65 degrees. What's the temperature outside? 90 degrees. So it's 90 minus 65, that's 25 degrees. Okay. What is the temperature of the cold reservoir? Well, it is 65 degrees, but remember it has to be in absolute temperature. 65 degrees plus 460 to make it to Rankine is 525. 525 Rankine inside this room divided by this temperature difference of 25 from outside to inside. 425 divided by 25 is 9, essentially. So 9 is the maximum coefficient of performance that a refrigeration cycle installed in this room between these two temperatures can attain. Okay. Remember that coefficients of performance can actually be larger than 1, unlike efficiencies, which always have to be below 1. In heat pump cycles, we also formulated a coefficient of performance. The coefficient of performance of a heat pump cycle, essentially a heater, is the amount of heat that we can reject to a hot temperature reservoir divided by the amount of work that we input into the system. So we use external work and we transform that into heat that we dump into a hot temperature reservoir. So let's think of the winter, for example. When my room is now I want it at 75 degrees and outside it's 50 degrees. Okay? So now my room is a hot temperature reservoir and the atmosphere outside is a cold temperature reservoir. It's at, let's say, 50 degrees. So my room is at 80 and the outside is at 50. And using that same principle or same rationale to look at the proportions of heat from the hot to the cold temperature reservoir to the temperatures of the hot and the cold temperature reservoir, I can establish that the maximum theoretical coefficient of performance of a heat pump cycle operating between two thermal reservoirs, TH and TC, is given by TH divided by TH minus TC. So let's do this analysis again. In the winter, when the temperature of my room is, let's say, 80 degrees, TH, and the temperature of the surroundings, of the atmosphere outside, is 50 degrees. The difference between the two is 30 degrees. The difference between the hot temperature reservoir, which is my room, and the outside is, let's say, 30. The temperature of my room is 80 degrees, but remember that has to be, all the temperatures have to be in absolute. So 80 degrees plus 460 is 540. So 540 divided by 30, which is the temperature difference, yields, let's say 540 divided by 30, divided by 30 is 540 divided by 30 is what, 18? 18 is the maximum coefficient of performance of a heat pump cycle installed in this room. So as you can see, heat pump cycles actually yield better coefficients of performance than refrigeration cycles. So it takes less energy to heat something up than to cool it down. Okay. All right, so let's look into some examples of the implementation of these ideas of the second law of thermo. Basically, the implications of the second law corollaries by Carnot, especially the second corollary, that leads to this equation of the maximum theoretical efficiency that a power cycle can attain. So let's look at a power cycle. And we are told that it's operating between two reservoirs, receiving an energy QH by heat transfer from a hot reservoir at 2000 Kelvin, and rejects energy QC by heat transfer to a cold temperature reservoir at 400 Kelvin. Okay. Now, this can be maybe a heat engine where the fuel is burning at 2000 Kelvin, and then it rejects energy to surroundings that are 400 Kelvin, 127 Celsius. Those surroundings right around the system. We are not concerned as to the mechanical operation of the system. We're concerned as to the thermodynamic conditions that lead to the generation of power in the system. Now, for each of the following cases, determine whether the cycle operates reversibly, irreversibly, or impossible. Okay, so we're given different values here. In this case, we're given QH and the W. In case B, we're given QH and QC. In case C, we're given W, which is the work, and QC, the heat rejection. And case D, we're given the Qn or QH and the efficiency. And we have to determine whether these cycles operating reversibly, irreversibly, or impossible. What is the difference between the three? Well, we should start by calculating the maximum theoretical efficiency, which is the Carnot efficiency, for which we have the two temperatures. We have the temperature of hot temperature reservoir and the cold thermal reservoir. We know the ratio of the two. That means that we can calculate the efficiency. Any data that we have out of observation that leads to an efficiency larger than that is impossible. If it's equal to that efficiency, it means that the cycle happens to or appears to be working reversibly. And if it's lower than that, then it appears the cycle is working irreversibly. All right? So we have this heat engine working in a cycle, is extracting energy from a hot temperature reservoir at 2000, this is QH, and it's rejecting energy, QC, to a cold temperature reservoir at 400 Kelvin. And in the process of doing so, it produces work. Okay. We have the efficiency of Carnot, which is the maximum theoretical efficiency, 1 minus Tc divided by Th. Remember, always in absolute temperatures. Now, if the efficiency that we find through data that was given to us is less than this Carnot efficiency that we calculate, then the cycle is possible and it's working irreversibly. So it's a realistic cycle, let's say heat engine. If it's equal to this Carnot efficiency, that means that the cycle is operating at the limit. It's reversible. It's perfect. So chances are that data is incorrect, because it's very hard to obtain that in real life situations. And if the efficiency that we obtain through this observation data is larger than the maximum theoretical efficiency, obviously that's not possible. It is the maximum theoretical efficiency for a reason. So the Carnot efficiency is 1 minus Tc over Th. 1 minus 400 Kelvin divided by 2000 Kelvin is 0.8. So that's 80% efficiency. This means that there's no way, under no circumstances, that any cycle that you can conceive, any heat engine that you can conceive, operating between these two thermal reservoirs can generate an efficiency larger than 80%. That is the maximum theoretical efficiency that you can yield. In case A, we were given, well, in observations, we were given that the net amount of work that it produces is 850 kilojoules, and the amount of work, or the amount of heat that we put into the system is 1,000 kilojoules. So we invest 1,000 kilojoules in energy by burning fuel, and we obtain from the cycle 850. That yields a thermal efficiency of 0.85. Something must have been wrong in these calculations, or this is flawed data, or somebody's lying to us, because it is impossible for a system operating between these two thermal reservoirs to yield an efficiency of 0.85, because the maximum theoretical limit is 0.8. So this is an impossible cycle. Then, in case B, we're given Qin and Qout. We're told that the energy extraction from the hot temperature reservoir is 2,000 kilojoules, and the energy rejection to the cold temperature reservoir is 400 kilojoules. That yields an efficiency of, well, remember that the efficiency is work net divided by Qn, and work net is Qn minus Qout, that's 1,600, 2,000 minus 400, divided by 2,000 yields an efficiency of 0.8. That is exactly the same as the maximum theoretical one, which means that this cycle appears to be working in reversible mode. It's ideal, it's perfect, okay, because it's yielding an efficiency that's identical to the maximum theoretical efficiency. Case C, we were given the work net and we were given Q out. We were given the heat rejection to the cold temperature reservoir. That's 500. We're given that W net is equal to 1600. Remember that the efficiency is W net divided by Qn. But remember also that W net is Qn minus Q out. Therefore, Qn is equal to W net plus Q out. W net is 1600, Q out is 500. 1600 plus 500 is 2100. So the amount of energy invested in this cycle, energy in, is 2100. The amount of work that we obtain is 1600. That yields an efficiency of 0.76. So that means that since this real efficiency is less than the maximum theoretical one, this is a process or a cycle that is perfectly possible and is operating in irreversible mode. It's yielding an efficiency less than the Carnot efficiency as expected. So this is kind of a realistic case. And case D, the last set of data that we were told or we were given, we were essentially given the efficiency directly. Somebody already did the calculations and calculator computed the efficiency of this cycle to be 30%. And since we have already calculated that the maximum theoretical efficiency of a cycle operating between these two thermal reservoirs is 0.8, it essentially means that this is a realistic cycle. Not only is realistic, it's operating irreversibly. So the conclusion on this one is that this is true, possible, and is irreversible. Okay? Okay, so let's look at another example in which we have a power cycle. And this power cycle is operating between two thermal reservoirs, one at 727 Celsius and another one at 127 Celsius. So we have the hot temperature reservoir and the cold temperature reservoir. For each case, determine if any principle of thermodynamics will be violated. And so far, the principle of thermodynamics that we know are the first law of thermodynamics and the second law of thermodynamics. The first law of thermodynamics is the conservation of energy. Basically, that the change in energy of a system can be affected by Q and W. So if we have a power cycle, all the delta U's will cancel out. So we'll have that the amount of work that we produce in a cycle is equal to the heat in minus the heat out. So we're given three cases. Case A, we're given a QH, which is Q in, equals 300 kilojoules. The W of the cycle is 160, that's the W net, and the QC is 140 kilojoules, that's the heat rejected to the cold temperature reservoir. Case B, the system absorbs 300 kilojoules from the hot temperature reservoir. It rejects 120 kilojoules to the cold temperature reservoir, and in the process of doing so, it produces 180 kilojoules of power, or work. In case C, the system apparently absorbs 300 kilojoules of energy from the hot temperature reservoir. It rejects 140 kilojoules of energy to the cold temperature reservoir, and in the process of doing so, it produces 170 kilojoules of work, mechanical work. So the first thing, illustrate the cycle. We are absorbing energy, or the cycle is absorbing energy from a hot temperature reservoir at 727 Celsius, and it's rejecting it to a cold temperature reservoir at 127 Celsius, and in the process of doing so, it generates work. So the equations that we have are the Carnot efficiency. When the cycle operates at the maximum theoretical efficiency, efficiency is 1 minus Tc over Th. Remember that those temperatures must be in absolute temperatures, not in Celsius. They must be converted into Kelvin. We know that the first law of thermal says that W net is equal to QH minus QC, or simply QH is equal to QC plus WN. That's how we can confirm or validate that the first law of thermal is being respected. Okay, it's being followed. This is how we can confirm, the first equation here is how we can confirm that the second law of thermal is being validated. It's being followed, it's being respected. And the efficiency is W net over QH. That's the standard or actual thermal efficiency. And we have three cases to compare. Now the Carnot efficiency of this cycle is 1 minus Tc over Th. Remember, Tc is 127 Celsius, but we have 273 to turn that into Kelvin. That's 400 Kelvin divided by 1000 Kelvin. 727 Celsius plus 273. That yields a maximum theoretical efficiency of 60%, or 0.6. That means that no power cycle operating between the temperatures of 127 and 727 Celsius can produce an energy, can produce an efficiency larger than 60%. In case A, we're given QH, QC, and the W of the cycle. And we know that the first law of thermal, conservation of energy, states that Wn is equal to QH minus QC, or simply QH is equal to WC plus, QH is equal to QC plus Wn. We were given 300 as QH, 140 as QC, heat rejection, and 160 as the net amount of work. And they actually equate. 140 plus 160 yields 300, so the first law of thermo is being satisfied. Okay, it's confirmed. Then we go into the second law of thermo. Let's calculate the efficiency. The thermal efficiency is the net amount of work divided by the heat input, which is QH. It's 160 divided by 300. That's 0.53. What is this? Well, this efficiency is definitely less than the maximum theoretical efficiency, and therefore this cycle is possible, is feasible, and it's irreversible. So the second law of thermo is confirmed. Okay, so now we confirm the first law of thermo, the second law of thermo. That means that this particular cycle and that data that is claimed is possible. Second law of thermo is satisfied as well. And the second case, case B, we were given QH as 300, we were given QC as 120, and we were given the net amount of work on the cycle as 180. Again, 120 plus 180 yields the same as QH, which is 300. So the first law of thermo is satisfied. There is energy balance. They equate in this particular cycle. Then if we calculate if we use the second law relationship, which the only one we have is the efficiency of Carnot, we compare the true efficiency to the efficiency of Carnot. The net amount of work is 180. The QH is 300. So the efficiency that this data claim yields is 0.6 or 60%. And as you can see, that is the same as the Carnot efficiency. So although it's the same, we say, well, this cycle is possible. It is satisfied. It is satisfied right on the line, but it's satisfied nonetheless. So this is not less than the efficiency of Carnot. It's equal to the efficiency of Carnot, but it's good enough to satisfy. So this is basically a reversible cycle. This exchange of energy between thermal reservoirs in order to produce work can actually be reversed and do exactly the opposite. And finally, case C, we're given the Qin or QH equal to 300, QC or Qout equals to 140, and we're given work that being produced at 140 kilojoules. As you can see, these ones do not match. QC 140 and W equals 170 yields a QH of 310. That's not the same as the value we're given. So there's energy leak. That means that the first law of thermo is not satisfied. First law of thermo is violated. The output is more than the input. That is not possible. And the work should have been 130 in particular, or some of the other data is incorrect. So there's no need to even check the second law of thermo. The fact that the first law of thermo is being violated, it already means even if the efficiency that you calculate through here, 140 divided by 300, is less than the Carnot efficiency, less than the maximum theoretical efficiency, it doesn't mean anything, because this particular cycle already violates one of the laws of thermodynamics. If you violate any of the laws, then the process or the cycle is not possible. It doesn't exist. Okay? So this is or was the introduction of the second law of thermodynamics. We also worked on some examples. And remember, the second law of thermodynamics doesn't come from a general conservation principle. It doesn't come from a universal conservation principle. It is just a set of statements and corollaries that are drawn directly out of observation of the operation of heat engines in particular. All right. So, and we're going to continue with these particular concept, and for the next few lectures we are going to extend the implications of the second law of thermodynamics, and we are going to introduce quantities that are going to help us measure that difference between the actual efficiency and the Carnot or maximum theoretical efficiency. Okay? The difference between that are the irreversibilities. So we're going to define a new property that will help us measure that will help us quantify that. So thank you for your attention, and I'll see you next lecture.